Ernesto for the introduction. I'd hope you would lower the expectation of the audience a bit. I'm not sure I can live up to what you said, but I'll do my best. It's especially an honor to speak here for Sam Gittler's 80th birthday, and also an honor of Jose Adem, two of Mexico's finest mathematicians. So I was asked that this should be talk to a broad audience. The title is Manifolds and Moduli.
Yes, I should warn you that the first lecture will be an open lecture for all of the
So it'll be a slightly different style from the previous lectures in the day if you went to those. So this will be the topic of all my 3 lectures, but today I'll just give a sort of an introduction to what do I mean by manifolds and moduli spaces. So, well, a manifold is often the solution to n minus d equations in n variables. A set of solutions. This is not quite the definition, but it's an approximation to a correct definition. I'll write some extra. Yes, thank you. Can you read this, by the way? So, first example you see in a class of manifolds is probably this equation. X squared plus y squared equals 1. This circle. And this is a one manifold. One-dimensional manifold. Let me write a few other examples. There are 2 variables x and y in one equation. If the equation is x plus y equals 1 instead, it looks very different. The coordinate axis and the set of solutions looks like this. Again, it's a one-dimensional manifold, sort of a one-dimensional object. More interesting equation, z squared plus 2 minus square root of x squared plus y squared equals 1. This is one equation in 3 variables, so this might be a 2-dimensional manifold, and it's a torus. So you draw it like this, donut-shaped thing, where the axis you could also have 0-dimensional manifolds. If you have 2 equations in 2 variables, the set of solutions to these 2 equations is not very difficult to solve. There's exactly 1 point in the origin, and that's a 0-dimensional manifold. So this is not quite the definition. You could write equations that don't, where the solutions sort of don't behave nicely. X squared equals y cubed. like this. Sort of a bad point at the origin. And here I should say I'm talking about smooth manifolds. This is sort of one-dimensional, but it's not a smooth manifold because it has this kink here. I won't write the exact definition. Most of you probably know. So you can't write an arbitrary set of equations. They should be sort of in general position. Or generic. But often, I mean, this is, I think, not an exaggeration to say that one of the key sources of manifolds is as solutions to equations. Yep. Yes, I'm getting to that in a second. Yes, so what I actually mean is a set of points that locally can be described by a set of equations. So, so a set of points Rn locally the set of solutions to this many smooth equations in n variables and condition on the derivatives. So when are two such things equal? Well, that's actually an important point for my talk, and especially the two following talks. They can be quite similar without being quite equal. So if you have another equation, x squared plus 2y squared equals 1, you get a different set of solutions. Get an ellipsis. So they're not equal. There are points on that one that are not on that one. But they're still quite similar. You can translate from one to the other by have a solution to this set of equations. You can divide y by square root of 2. Or multiply, I think. One of those. And conversely, if you have a solution to this equation, you can multiply y by square root of 2. So these manifolds are not equal, but they're called what's called diffeomorphic. And I want to distinguish between being equal and being diffeomorphic. Equality means equal, and diffeomorphic means the existence of a diffeomorphism. Well, you know the definition. No. Nope, not an ambient. So the study of manifolds has been a driving force in topology since at least the 50s, or well, before that. So this is not actually what I will talk about, but I want to mention the problem of classification. It's like classification in in the rest of science, if you want to classify if you want to classify, I don't know, animals or something, you don't want to say there's a dog there, and there's a dog there, and there's a cat there, and there's another cat. You want to say what's the types of animals you can have. There's cats and dogs and etc. You can ask the same question for manifolds. So find a list of manifolds. So what's that? Any manifold is diffeomorphic to precisely one in the list. So it's a catalog of all the possible manifolds you can have up to diffeomorphism. This is sort of, you can't quite solve that if you ask it in this generality. And in any case, it's not really what I want to talk about here. But let me introduce a few more technical terms. So I really only want to talk about manifolds that are compact. So, well, what I said here did not allow boundary, but yes, manifolds without boundary. What I said before was the definition of a manifold without boundary anyway. So compact, roughly speaking, means that you rule out two phenomena. So, here's an example of a manifold that's not compact. This set of solutions. So this is an interval. And it's not compact because it's not closed. So there are points that are not solutions, but there are solutions arbitrarily close. There's a point here. This is not in the manifold. But there are points in the manifold that are arbitrarily closed, arbitrarily close. So that's not compact. And the other way you can be not compact is if it's not bounded. So what I wrote before, x plus y equals 1. You can, there's no upper bound to how far away from the origin the points, the solution can be. So as I mentioned to Dennis's question, the criterion is that locally it can be described by a set of equations. The circle, there's 2 circles, there's 3 circles, and there's the empty set, and that's in fact a complete list. Any compact 1 manifold is diffeomorphic to precisely 1 in this list. But in general, it's a difficult question. imagine one more result, or two more maybe. Two-dimensional manifolds. Well, that was the torus I wrote before. Z squared plus 2 minus square root x squared plus y squared equals 1. That's a sphere. X squared plus y squared plus z squared equals 1. Empty set again. That's what you get by gluing two tori together. You can glue multiple tori together. This is not quite a complete list, but this is a complete list of smooth, compact two manifolds which satisfy two extra conditions. They should be connected, so you can get from any point to another one, staying inside the manifold. And orientable. Orientable means that it does not contain the Mobius band. The Mobius band is not orientable. Anyway, so you there's more or less there's a complete list known there. But that's not really my main topic. This was there's a related question. So whether or not you have a complete list, you always have a partial list. You can sort of start writing down all the manifolds you can think of. Then you can pick one of them in your list and say, well, you can study the collection of manifolds that are diffeomorphic to that one. So it's sort of going in a different direction. Given a complete or partial. Manifolds. You can say, oh, I'm especially interested in this one. And as I explained before, there are many manifolds that are equal that are not diffeomorphic. So if you've picked a particular element in your list, there are many manifolds that are diffeomorphic to that. And we could try to consider the collection of all those manifolds of that type. So in the vague analogy I made before, it's like some biologists try to classify animals or flowers or something, and others say, oh, I only care about whatever, chihuahuas, and I'm going to study how is the population of chihuahuas. So let me, or something, maybe some extinct species. So you can say pick one, maybe maybe you like dimension 2, you say, I pick this one, and there are many manifolds diffeomorphic to that. What does the collection of all those look like? I should maybe have made one more list, namely D equals 0. So I mentioned one zero-dimensional manifold, namely the point. You could also take 2 points, 3 points, etc. And that's also a complete list. Collection of all manifolds diffeomorphic to that. Well, what do I mean by, well, there are many words I haven't explained. What do I mean by all manifolds diffeomorphic to that, and what do I mean by study? So let me try to give some examples. I won't say anything terribly precise in this lecture, but you can come to my next 2 lectures if you want something more precise. And something maybe slightly surprising, in a way, I don't know, is that even in the case where the individual manifolds are sort of not very interesting, there's not a lot of geometry to the manifolds, the collection of all what manifolds can you imagine that are diffeomorphic to that one? Well, that's just a subset of Rn with 2 points. Here's one. Subset of the plane. And here's another one. The collection of all of them forms a kind of space called a, well, in this context it's called a configuration space, but more generally I'd like to call it a moduli space. They're often called B, in this case R2, 2. This is the collection of all 2-point subsets of R2. You can imagine how the notation works. You can put an n there and a k there, and it's k-point subsets of Rn. So in this very low case, you can sort of see what the space looks like. You can parameterize all of them. If you want to specify a 2-point subset, one thing you could do is say, where's the center of mass? How far apart are they? And what's the angle, the line between them makes with the x-axis? Parameterized. X, y. Coordinates of the center of mass. Z, distance from x to y. And an angle between 0 and 180 degrees. The angle that the line between the 2 points makes with the x-axis. So here it would be pretty close to 180 degrees. degrees means the same thing as 0 degrees. So here you can sort of say, okay, it's maybe not the most interesting space in the world, but nevertheless it's way more interesting than the 2-point space that we're parameterizing. And that's a general phenomenon that that if you well, we'll see more of that. So let's see. So more generally, let's have okay. Understanding that space, as I said, is sort of doable, but it's still a lot harder than classifying the underlying zero manifolds that we're parameterizing. So what kind of questions do I want to ask about these spaces? Well, I'm mainly interested in the topology. So, what is the topology? Such spaces. Well, maybe I should so this is a question. It's mostly known in this case. The main topic of my next 2 lectures will be higher dimensional analogs of this question. So, so this is what I would call the collection of all zero-dimensional manifolds, diffeomorphic to k points. But you could also pick some manifold of higher dimension and look at the collection of all manifolds of diffeomorphic to that. So this is all often called a configuration space. Yep. Well, I mean, you can ask the question also for finite n, but if you can't answer that, you could let it go to infinity. So if you have a manifold of higher dimension, you could replace, so K here really was a stand-in for K-point subsets. A fancy way of saying that would be zero-dimensional manifolds of a certain diffeomorphism type. So if you say it that way, you can generalize it to higher dimensions. So given some maybe given a compact in. What is the topology of the collection of all manifolds diffeomorphic to that one. this question is a special case of that one. And again, it's sort of, I think of it as kind of orthogonal to the classification question. Classification about finding a list of manifolds sort of up to diffeomorphism. And this question is about studying the collection of all manifolds inside one diffeomorphism type. Yep. Yeah, they don't coincide. Yep. 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 Right. Subset means no multiplicity. So it has the structure of an infinite dimensional manifold. It certainly does not have the structure of a finite dimensional manifold. So you're not going to be able to approach it this way, somehow find a parameterization and say, oh, this is what the collection looks like, and you can maybe see there's kind of a circle happening here. That type of approach is not going to work here, so you need something more sophisticated. So you should say that. So first problem. Can't parameterize. I didn't give this a name, but maybe in this lecture I'll call it B of Rn, comma M, in analogy with usual notation for configuration spaces. And it is in any sense, this collection will be infinite dimensional. So you're not going to understand it by just trying to imagine what does it look like unless. Yep, yep, yep. Yes, there's also, yes. A quick definition would be the space of embeddings of M into Rn divided by the diffeomorphism group. Since there's so many mathematicians here anyway, let me write that. So we're supposed to end 50 past? Oh, okay, okay, good. Yep, that's fine. Yep, yes, right. Hmm? Yeah, yeah, yeah. Yeah, sort of, well. But that's also not going to play a role that it's a manifold or not, at least not in anything I've said about it. So, okay, so that's the question that, this is what I mean by a moduli space, by the way. You could call it you might call it a configuration space of manifolds or something, but I usually call it that. So more generally, we can ask what is the topology of the of that space. Well, here it's even more true that understanding the topology of that kind of space is a lot harder than trying to classify manifolds of the type you're talking about. So in the two-dimensional case, which is where the word moduli space comes from, in the two-dimensional case, we pretty much, I mean, we have a list of all manifolds. So here's the list of connected oriented ones. This is called one surface, this two surface. Sigma 1, sigma 2, etc. The space of all manifolds in Rn, diffeomorphic to a genus G surface. We know very far from everything about it, but we especially know a lot when N and G are both big. So in the remaining time, let me try to explain a little bit more about that and say what do I mean by understanding the topology. So by understanding the topology, so let me go back to the zero-dimensional case again. This case should have said a lot of. I've learned about that. I learned in Fred Cohen's thesis, I think. By topology, I really mean homology. So this was supposed to be a broad talk, and if you've never heard about homology before, then I'm afraid I'm not really going to define it here. But let me say a few words. Space X. Homology is some kind of measure of how many holes it has. And maybe the only thing I should say is that there are different kinds of holes you can make in an object. If you have a solid box, something, you could take a drill and drill a hole through it. One kind of hole. Or you could create some kind of bubble in the middle. That I also call a hole. Or you could take an axe and cut a hole in it. Cut it into two pieces. That you might also call you made a hole in the middle. And the different homologies. This kind of hole is measured by the first homology. This kind of hole is measured by the second homology. This is measured by the zeroth homology. And for higher dimensional objects, you sort of can continue as a sequence of groups counting holes of different dimensions. Yes. There's an associated measure called Betty number. X. Well, I won't tell you the definition, but it's supposed to measure the number of n-dimensional holes. So what I mean by understand the topology is understand the homology or the Betty numbers of the spaces. And that's, if I was only talking about the underlying manifolds, that would be a very easy question. But understanding the homology of the collection of all manifolds of a given type is quite difficult, even in the zero-dimensional case. Does it have a somewhat complicated answer? answer is known. There's a quite complete answer known in 0 dimensions. But I want to say two things that are known that's going to lead up to my next two lectures. So there are two important ideas. So about H. As I said, there's a whole sequence. This continues H1, H0, 1, 2, but you can also take bigger numbers of the configuration space, K points in Rn. Or ideas / theorems. The first is that turns out to be independent of n and k as long as they're big compared to I. Should probably be bigger than 2I or something. We're just right. This means something like k should be bigger than 2I and n should be bigger than I, something like that. But as long as they're large, it doesn't really matter what they are. And the second idea / theorem is that whatever the answer is, in the range where it does not depend on n and k, it's the same as some other space. Actually, it's even true if I raise the n here. So it's independent of k as long as k is big compared to n. So for k big compared to I, it's the same. So it meaning the homology or the number of this measure for the number of holes is the same as it's the same as the homology of a space of functions. So HI of K is the same as HI of another space, or loops n as n, where loops n as n is the space of continuous functions from Sn to Sn, with the property that they take, well, the base point preserving. So Sn, I guess I didn't say what that is. The solutions to x1 squared plus up to xn plus 1 squared is 1. This is a particular point, and it should take that point to itself. So, well, I'll talk more about that next two lectures. I'll say the slogan is homological stability. The homology is stable in the sense that it doesn't change when you make k bigger, as long as it's not too small. And point two, I'll say the slogan is stable homology. once the homology stabilizes, what is it? This will be the topic of my next lecture. And this will be the topic of the third lecture. Yep, yep. So, as I said, I wanted to mention the zero-dimensional case because I think it is an analog. In that case, actually a lot more is known. As I said, thesis. But these two particular features can be generalized to moduli spaces of high-dimensional manifolds. So let me stop here. First of all, I was not looking at the space of embeddings. I was looking at this modulo diffeomorphisms. I mean, you can ask both questions. If n is big, it's sort of the same as, it also stabilizes as a function of n. And to be honest, I think that's the case where I actually have some theorems to talk about. But it's a meaningful question also for finite n. Oh, is that answers the question?
De rayas.